Good morning, everybody. Today we are going to be finishing the concepts of chapter 4, which is the last material in this week's exam. Remember that the exam opens at midnight on Friday, and it needs to be submitted by Saturday at 11:59 p.m. Make sure that you also submit all the other assignments that you have during this week. In yesterday's class, the last concept that we were studying was understanding that when we have an element, the basic unit of it is called an atom. We also went over the historical precedents that tells us how it was discovered that these elements were formed by these atoms. And one of the things that we learned is that even though the atom is going to be the smallest unit, the smallest particle, it has what are called subatomic particles. And these subatomic particles are known as protons, neutrons, and electrons. The information of protons, neutrons, and electrons for each of the elements in the periodic table, it has been incorporated into the information that we get on each of the boxes for the periodic table. As you can see here, the atomic number for an element, which is placed right above the symbol for the elements in the periodic table, not only gives us the number of protons, but it gives us the number of electrons. And that is going to be when we talk about ground state elements, meaning that all the elements in the periodic table are not losing protons yet. That is a concept that we are going to see next week in chapter 6. In addition, if you're trying to find the number of neutrons, as you can see in the notes that I have above the slide, because we know that the mass of a particular element equals the number of protons plus the number of neutrons. If we're trying to define the number of neutrons for a particular element, understand that we have to take the atomic mass or mass number, which has been rounded to a whole number, and we're going to be subtracting it from the atomic number. So in yesterday's class, we did one of the problems from, as you can see here, the part C of the in-class worksheet, okay? So at this time, I'm going to give you guys just a few minutes. And as you can see, we are going to now proceed to fill in the information for chlorine. So let's put the symbol for it. What is going to be its mass number, its number of protons, number of neutrons, and number of electrons. So I'll give you guys 1 minute to do that. Let's get started. What is the symbol for the element chlorine? Let's put it in the chat. Great job. Capital C, small l. Now, we know that the atomic number for this element is 17. So that means that that 17 is going to equal the number of protons and number of electrons. So there's going to be 17 protons and 17 electrons, okay? Now, taking this into account, if we put it to 2 decimal places, what's going to be the atomic mass for it? And that's what we put in parentheses. What's the atomic mass for chlorine? Excellent. So like you guys were placing there, the atomic mass is going to be 35.45 AMU. Now, that number, when we round it to a whole number, is going to be a value of 35. Okay. Now, the only piece missing here is going to be the number of neutrons. So in order to find the neutrons, what we're going to do is subtract the mass number from the number of protons. So if we do 35 minus 17, how many neutrons are there? Great job. There's 18. Any questions at this time? If you're giving any information from what we find in the periodic table in terms of the atomic number or the mass number or the symbol or the name, can we fill the following information? Go ahead, Kayla.
Is the number of protons and the number of electrons always the same as the atomic number?
Is going to be always the same for the atomic number as long as we're talking about ground state elements. For this exam, we are only dealing with ground state elements. When we introduce the concepts of chapter 6, which is going to be next week, we're going to see how elements in the periodic table actually can lose different protons or gain electrons, or what am I doing? Sorry about that. So elements can actually lose electrons or gain electrons. So it's not that they don't lose protons, they lose electrons. So they either going to lose electrons or gain electrons. And based on that, we are going to see that then because the numbers change, they're going to become charged species. And when they become charged species, they're called ions. So that is something that we deal next week. For the purposes of the exam this weekend, you guys are only dealing with ground state elements, which means that the number of protons and electrons are going to match the atomic number.
Okay, thank you.
No problem. So the 0.45 in Cl come from, so what I put in the parentheses is actually the atomic mass. That's going to be the mass that shows up in the periodic table. So understand that mass number is what I consider when we round it, but then atomic mass is what shows up in the periodic table, like below the symbol. So if you are using the periodic table that I uploaded to Canvas, you will see that below the symbol of Cl, you will see 35.453. So I just rounded to 2 decimal places because I have a small table. The reason why we have to round it to a whole number is because when it comes to subatomic particles, we don't have partial subatomic particles. It is known through experimentation that these subatomic particles, when they exist in the different elements, they are not less than 1. So that's why we have to round it to a whole number. Any other questions? Excellent. Those were great observations, you guys. Now, one of the things is that these elements that are found in nature or have been created in the laboratory sometimes can have different flavors. So I utilize the analogy of, like, if you go to the supermarket and you're trying to buy vanilla ice cream, okay? So when you try to buy vanilla ice cream, specifically, if you are going through the aisles and you're looking like I know Breyers has this, like you can buy vanilla bean ice cream, you can buy Mexican vanilla, French vanilla, homemade vanilla. So there's a whole bunch of different ice creams, but they're all vanilla, correct? So when it comes to elements, you can have what are called isotopes. And isotopes are going to be atoms of the same element. So we're all talking about the same element. Again, utilizing the analogy of ice cream. These are all vanilla ice creams. It's just that in terms of chemistry, isotopes are going to have different atomic mass, okay? So we can observe in table 4.7 that specifically, when you search in the world for what kind of magnesium is out there on Earth, we can have magnesium 24, magnesium 25, or magnesium 26. Again, we are all talking about magnesium. So the number of protons and the number of electrons is the same, 12, because specifically that is the atomic number for magnesium. Now, each of these isotopes, because they have different number of neutrons, they're going to have a different mass number. So when we look at this, we can observe that these different magnesiums all have the same number of protons and electrons, but when it comes to the neutrons, magnesium 24 only has 12 neutrons, magnesium 25 only has 13 neutrons, and magnesium 26 only has 14 neutrons. And then we can even see of the mass, the atomic mass of them, how it is 23.99, 24.99, and 25.28. Now, understand that when it comes to this data has been gathered in the laboratory. Similarly, when they have actually sampled around, in the world around us, what is the most prevalent magnesium, you can see that we have been offered in this table the percent abundance. And the percent abundance tells us, how common is to find a particular isotope. So, as you can see here, when we look at the percent abundance, comparing magnesium 24, 25, and 26, magnesium 24 has the highest percent abundance at 78.70. So, having a high percent abundance, that means that out of all of these isotopes of magnesium, a magnesium 24 is the one that is the most common, okay? Now, you can see that when it comes to the atomic symbol in this table, we are writing each of these isotopes in a particular notation. So understand that this notation is what we know as isotopic notation. And you guys are able to write isotopic notation for any element in the periodic table or any isotope of an element in the periodic table. This is how we represent these isotopes in isotopic notation. As you can see here, we have a particular element. So what is element U? What does that stand for? What's element U? Excellent, that's uranium. So uranium, as you can see here, we have the symbol of the element written. And then we're going to have two numbers written next to the symbol. And these numbers in isotopic notation are written on the left side of the chemical element. The one on the top is going to be the mass number, while the number in the bottom is going to be the atomic number. So what does this mean? That if you're given the isotopic notation for a particular isotope, you can determine by looking at this value, what is going to be the number of protons or the number of electrons. And because this is the mass number, then you can say mass number minus atomic number is going to equal your neutrons. So as you can see, even if you're given isotopic notation, you can derive the information that we were talking about for the elements in the periodic table. So now we are going to go back into the table that we were working with, and we are going to finalize some of the information that we have here. So let's go through the following. Let me just zoom in on it. So let's work now on the third row and the fourth row, okay? And let's do it together as a group. So we have an element that have the symbol Si, okay? What is the name of the element with symbol Si? Great job. This is silicon, okay? What is the atomic number of silicon? Great job. So since we know the atomic number, that's going to be the number of protons and the number of electrons, okay? You are given here the mass number for this silicon, which is 28. You can see that in parentheses, we actually put the atomic mass for this silicon, okay? But since we know the mass number and we know the number of protons, how many neutrons do we have of silicon? Excellent job. Let's do the last example. In the last example, you're given the number of protons and the number of neutrons for a particular element. Great job, you guys. Excellent. So if you're given that information, okay, because of the number of protons, you know that the atomic number of this is going to be that number of protons. So element 29, that is copper. Okay, now I want to specify something when it comes to this. Observe that I gave you a number of protons and a number of neutrons here. So when it comes to the mass number, okay, and you are given protons and neutrons, what we're going to do is add those two values. So you're going to say 29 plus 36. That is going to be 65 as a mass number, okay? Now, when we look at the periodic table, what's going to be the atomic mass that is in the periodic table? Rounded to 2 decimal places. Excellent. 63.55 AMU. So I want you guys to stay here for a second and all of a sudden not be like, oh, Dr. Luz messed up. No, I did not. What happens here is that understand that when it comes to atomic mass, this is a calculated weighted average of the isotopes for an element. This summer, we are not going to learn how to get that average atomic mass for the elements. But if you go into the textbook, it will tell you how to do those calculations. Pretty much because this is going to be a weighted average. What you do is that you multiply the mass of the isotope times the percent abundance, and then you add those values for every single one of the isotopes for that particular element, and that's how you obtain that atomic mass, okay? So in the case of copper, and the copper that I'm illustrating here, let me just make a note. The copper in this example is an isotope, okay? So that means that this is not going to be copper 64 or copper 63. This is copper 65, and you know that we're talking about copper 65 because that number came from the addition of these two values. We are only going to be changing that mass number that is going to be different from the atomic mass if I give you protons and neutrons. You may not do it for elements as we have seen in the examples above. Okay? So to finish up the information that we need to incorporate in this row, since we know that there's 29 protons, there's going to be 29 electrons. Any questions on how to determine symbol, name, atomic number, mass number, protons, neutrons, and electrons for any element in the periodic table? Go ahead with your question. To answer one of the questions in the chat, when it comes to elements, not all elements have isotopes. There are some elements that only have one form of it. So for example, helium is only found as helium-4. Other ones may have like two flavors. So for example, chlorine is like chlorine 35 and 37, but there are some elements like sulfur. Sulfur, I think, has like 3 or 4 different isotopes. So it depends. Now, the man-made elements, we don't have a lot of information for them, just because they were created in the laboratory. So this whole idea of isotopes, it's mainly for the ones that we have samples on Earth, because we can actually determine the percent abundance. When you look at a periodic table from recent times in which you look at the atomic mass of elements that are created in the laboratory, they don't even have decimal places, because I think since they are so short-lived and we don't even have compounds that are made with them, so we have very limited data when it comes to it. So when it comes, there's another question in the chat. Let me just read the question. So we always have to calculate mass number with protons and neutrons before checking the AMU on the periodic table. That will depend on the information given. As you can see in examples 1 through 3, because you have information that limit you just to know the atomic number and you derived everything from the atomic number, or you were given the symbol and the mass number and you derive everything from it, then we are going to base it on the periodic table. In the last example, for the one for copper, the reason why the mass number is going to be different from the atomic number is because I provided protons and neutrons to illustrate that copper actually can have another isotope. So only in the instance in which I provide protons and neutrons, then understand that the mass number may not equal to the number that you have as an atomic mass in the periodic table. Excellent. So let's actually proceed now to write the isotopic notation of these 4 elements that we have in this table. Understand that in the in-class worksheet, this table is more extensive, okay? So let me just number these. So this is number 1, this is number 2, this is number 3, this is number 4. Let me just write number 4 here. So for beryllium, when we're trying to write its isotopic notation, we're going to write the symbol. And on the upper left corner, we're going to put the mass number, which is a value of 9. Okay. Then in the bottom of that, we are going to put the atomic number, which is a value of 4. Next one, chlorine. We're going to have its symbol, which is Cl. In the upper left corner, we're going to put 35. In the bottom left corner, we're going to put the value of 17. Okay. Number 3, silicon. Its symbol is Si. So what value do I put in the top left corner? What number do I put? Excellent job. I do 28 here. And in the bottom? Great. And lastly, I have copper. Its symbol is Cu. So what number do I put in the top left corner? And what about the bottom left corner? Excellent job, you guys. Any questions about determining the number of protons, neutrons, and electrons, determining atomic number, mass number, the symbol or isotopic notation for any element in the periodic table? So the last 2 columns, valence electrons and electron dot symbols, we're going to deal with that in a few moments, once I introduce some concepts, okay? Let me just
Perfect. Question.
Yeah, go ahead, Gina.
There, on the slide prior to that, the isotopes and atomic mass, where the mass number, verify the formula. It's on your other, it's on the slide after this one, the 4.5 isotopes and atomic mass. I wasn't able to write it.
Wait, say that again because you were getting cut off.
On, I think, slide 25, the isotopes and atomic mass, you were, there was a formula you had written for 2 getting the mass number, and it's mass number, but that gives you the mass number. I know that sounds confusing, but there's on the next slide, the 4.5 isotopes, there's like that you wrote. There you go. So it's mass number minus atomic number gives you neutrons.
Uh-huh.
Okay, I just wanted to make sure I wrote that down correctly. Thank you.
Yes, So neutrons
Thank
is
you.
always take the mass number minus the atomic number. That always gives the neutron.
Thank you.
No problem. Any other questions? Excellent. So now we are going to move on to section 4.6, which we are going to learn specifically about the electrons' energy levels. So yesterday in class, when I introduced the concept of how do we know that these atoms are going to be specifically the smallest part of the particle, the smallest part of an element, we learned how there were so many experiments that lead up to early atomic theory, which is where we learned that through all the experimentation that we have here, that we know that each one of those atoms has those protons, those neutrons, those electrons. But up until the end of early atomic theory, we didn't give any location to the electrons. So in section 4.6, then we're going to focus in that modern atomic theory, in which we are going to discuss the contributions of Niels Bohr and also Schrödinger. So going back to understanding this, remember, by the end of early atomic theory, we don't know if there is a particular location for the electrons. We just know that they are going to be around the nucleus somehow. Why is it important that we know where the electrons are? Because depending on where the electrons are in an element, then that is what's going to determine for that particular element what is going to be its physical properties and its chemical properties. Okay, so the images that you see here on this slide, the one on the left, where you see that sodium nucleus and those dots and those rings, that is going to be more of the Bohr model of how he observed the elements. And the image on the right is actually going to be how we think of the location of the electrons currently. But let's actually talk about both models and why they were so important for us to understand now where the electrons live on each of the atoms for the elements in the periodic table. So let's first talk about the contributions of Niels Bohr. As you can see, Niels Bohr around 1910 explained how the structure of the atom changes when it actually undergoes energy transitions. And this is the experiment that he actually sees. So let's just focus on the slide on this top part. So Niels Bohr was doing an experiment in which he actually utilized a tube that contained hydrogen gas. So at this time, he is just dealing with a molecule that is sharing electrons because it's hydrogen gas, but because he is studying specifically hydrogen, okay? How many electrons does hydrogen have? How many electrons? Excellent job, only one electron. So whatever observation he's doing is based on the idea that I'm looking at an element that has one electron. So he took a hydrogen lamp, which you can see illustrated here. And then that once those hydrogen atoms are excited, are going to be emitting light. That light, he actually passed through a series of lenses and prisms, and understand that utilizing a photographic plate, he was able to take that light from that hydrogen lamp and observe that there were particular lines that were obtained from passing that light through lenses and through a prism. So then he started thinking, okay, if my hydrogen is able to produce these lines and create a line spectrum, at these particular wavelengths, this means that the electron that lives in a hydrogen is going to have different transitions that allows the emission of these different color lights. So when he started rationalizing why that is, then he developed a model in which he said, okay, the energy that it is in an atom is going to exist on what I'm going to call a quantized energy level. So he hypothesized that these electrons are going to be living in what he called orbits. So these are going to be areas of, if we think about how planets orbit around the sun. And he said, okay, since we know that the electrons are going to be around that positive nucleus in the atom, then those different quantized energy levels where my electrons live, I'm going to make them and designate numbers for the levels. So think about it of this kind of like floors in a building. You have n equals 1, first floor, n equals 2, second floor, n equals 3, third floor, n equals 4, fourth floor, so on and so forth. Then he rationalized, okay, since we understand by now through collaborations with physicists that whenever photons of light are going to be emitting different colors is because they go through the process of excitation and relaxation. Okay, and overall what we see here is that in the process of excitation, we're going to have an electron that absorbs energy. It moves from, think about it, a lower floor to a higher floor. So it goes from, let's say in this example, from n equals 1 to n equals 3. This is just to give an example. Now, when this electron moves to a higher state, at some point it has to chill. It cannot be excited all day long. So when it needs to relax, that's when it goes through the process of relaxation. Relaxation is when it goes from excited state to a lower energy level. So if it was at n equals 3, then it can go all the way down to 1. Or like you can see in the example, it can go from the third level to the second level. Now, what happens in the process of relaxation is that light is where is emitted. So understand that in excitation, energy is absorbed, but in relaxation, my light is emitted. So through there, he was able to rationalize, okay, so that single electron specifically is going to give rise to different transitions that make these 4 lines, okay? And I'm not going to go through the specifics in the math of where do we actually see the ranges, all of that you do in physical chemistry. So everybody was excited about that theory. That theory was, covering a lot of people's bases. It was great. It explained hydrogen very well, but it encountered a problem. His theory, his mathematical equations only work for hydrogen. Once you look at the line spectrums, and I have them here, for lithium, for oxygen, for carbon, for nitrogen, for neon, the whole theory created about Bohr in his hydrogen experiment did not work. Because you can see here for helium, there's multiple lines, lithium, multiple lines. So as we are increasing the number of electrons, and then if we compare these atoms to hydrogen, helium only has 2 electrons. Lithium has 3 electrons. Oxygen has 8 electrons. Carbon, specifically, has 6 electrons. Then the line spectrums get more complicated. His equations were not working. Okay. So the idea of having electrons in quantized energy level was good. So understand that not everything went to trash. Niels Bohr actually did a very important contribution, because having the idea that these electrons lived in specific energy levels, okay, and had these transitions was very important for the next theory, which is the quantum mechanical model of the atom. Now, Erwin Schrödinger used the idea of quantized energy levels. The difference between Niels Bohr and Erwin Schrödinger is just that Schrödinger made much better equations to define where the electrons are. Now, instead of thinking that electrons are going to orbit around the nucleus like planets orbit around the sun, Erwin Schrödinger said, you know what, I think electrons are going to be the subatomic particles that are going to be moving more. And when they move more, they actually create what is called clouds of probabilities. And these clouds of probability or probability maps is what is called an orbital. Okay, it's not an orbit, but an orbital. Okay, so whenever we're doing electron configurations in any of the chemistry courses, or if you have learned that concept, what you are actually defining is in these probability maps created by Erwin Schrödinger almost 100 years ago, the chances of finding an electron within the map that he created with his equations, and again, we are not going to go over the math, it is complex. We can find an electron accurately 90% of the time. So far, still in 2022, we utilize these probability maps to define where's the location of the electrons in a particular atom, okay? So these images that you see in the slide are actually the probability maps. In other words, the orbitals of where we can find an electron. So I'm going to do some markings here. First, I'm going to separate all of these to just talk about the different shapes. Okay, so in the quantum mechanical model of the atom, understand that all these shapes are defined by a letter. Now, for those of you that are asking, why is it called this particular letter? This is something that was how they defined it, okay? So the first one, which is a circle, this is called the s orbital. This second crew, this is called the p orbital. We also have d orbitals, and we have f orbitals. Okay, those are the 4 different maps that we have, S, P, D, and F. Now, on each of these maps, we are talking about the presence of, or they can hold up to, is what I'm trying to say, 2 electrons. So the maximum number of electrons that each of them can hold is 2. So what I mean by that is that this holds 2 electrons. This holds 2, this holds 2, this holds 2. And I'm just going to finish filling them up. Each of them gets filled by a maximum of 2 electrons. Are they always going to be filled? No, it depends on the electrons that a particular atom has. But I'm talking about maximums here, okay? So given the idea that an s orbital, there's only 1 map and it can hold 2 electrons, then that means that the maximum number of electrons that you can find at an s orbital is going to be 2. in a p orbital, because each of those shapes, each of those probability maps can hold 2, then that means that there are 6 electrons there, okay? How many do you think are going to be the maximum that can be held by a d orbital? Great job, 10. What about an f orbital? Excellent, 14. For those students are like, okay, where are you guys getting that 10 and that 14? For the 10 is just 2 plus 2 plus 2 plus 2 plus 2. For the 14, again, we have 2 electrons, 7 times, that's where we got the 14, okay? Now, all of this information, it is important because where these electrons live is going to depend on the energy levels, and it's going to depend on how many electrons we are talking about. And guess what? All of this is incorporated into the periodic table. So the electron configurations, what they are giving us in terms of information is where is the location and the distribution of the electrons in a particular atom. The orbitals are not filled randomly. All of this has been proven experimentally. And you can see that when the orbitals are filled, you start at 1s, then you move to 2s, then you move to 2p, then you move to 3s, then you move to 3p, then 4s, then 3d, then 4p, then 5s, then 4d, so on and so forth, okay? When it comes to examination for Chemistry 104, any electron configuration up to barium is fair game. I tend not to give you guys the F orbitals because that one becomes a little bit funky because the F orbitals are within part of the D. And so understand that I always tell students up to element 56, any electron configuration is fair game. Now, since we know that these orbitals are filled in this manner, all of this information is also incorporated into the periodic table. So the value that you guys see right here, this 1, this 2, this 3, 4, this 3, this 4, these guys represent the periods in the periodic table. So this is period 1, this is period 2, period 3, period 4, 5, 6, 7. So the largest number that we can find before the letters S, P, D, or F, depending on the orbital, could be up to 7. Now, there are some orbitals that we don't get up to 7 just because we haven't discovered elements there yet, okay? So understand, again, that value that I highlighted in green refers to the period in the periodic table. The other information that you can see here is that the periodic table can be divided into blocks, meaning that there's an area of the periodic table that is called the S block. That's the circle shape. Right here in this peach color, all of this is actually where the d orbital electrons, and you can see it there, 3d, 4d, 5d, 6d. And then from boron to neon, that area where we have metalloids, we have very few metals, and we have non-metals, those is where we have the p orbitals. And you can see it in the designation that we have in this periodic table. Now, how are we going to utilize all of this information to do problems in the exam? Well, when it comes to these problems, there's 2 ways that you guys can target it, okay? You can see here that in part E of the in-class worksheet, it says, determine the element name and symbol for each of the following electron configurations, considering them as a neutral atom. So what does this mean? There's two ways that we can approach this. And I'm going to teach you guys both ways on how to approach this. I'm going to do the long one first and then the short one. Use the one that works for you, okay? So you can see here how it says, oh, my electron configuration is 1s2, 2s2, 2p1. So if I focus on this periodic table, I'm going to say, okay, so in that electron configuration, I'm going 1s2, so I'm covering both of that. I'm doing 2 boxes of the 2s, okay? And then you can see that the last one is 2p1. So out of the 2p, I get 1 box. And we're always filling this by row from left to right, okay? So after I go through my process, I see that I land on boron, okay? So that is the element. So that's the long way to do this. The symbol is letter B. You guys, this is the easy way. You're going to take 2 plus 2 plus 1. When you do 2 plus 2 plus 1, that's going to be the number of electrons in an element. So in this case, it is a 5. Remember that the number of electrons in an element also equals the atomic number. So who is the element that has atomic number of 5? Boron. So choose the method that is important for you, that is makes sense to you. In my case, I like adding. I like the second method. I think it is easier. As long as you don't mess up the math, you'll be good. So let's utilize that second method to do number 2, okay? So how many electrons are in that electron configuration? How many electrons? Let's put it in the chat. Great job. So when we add 2 plus 2 plus 6 plus 2 plus 2, that gives us 14 electrons. What is the element that has 14 electrons? Meaning that it has an atomic number of 14. As you guys saw, it is silicon. Should we do one more? Excellent. Number 3. We have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. So when we add these numbers, what do we add to? 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 2. Excellent. We have 22 electrons. Remember, we're going to look at the atomic number of that. Oh, sorry, I didn't write in the answer here. So who has 22 electrons? Excellent job. Titanium, which the symbol is Ti. Now, I want to mention this for my students that are going to move on to other chemistry classes, because maybe in other chemistry classes, you will be prompted to actually write the electron configurations given the name of an element. So when you are prompted to do that, understand that you can utilize the periodic table to actually write the electron configuration. You always start here at 1, the S block, 1, 2 boxes. That's where that comes from. So let me just do some markings here. Let me just erase some of the things here to illustrate how we actually develop these. I'm just going to do to the best of my abilities. Let me do boron because it'll be easier to highlight since it has less electrons. Where we came up with that. So just in case, if you have other chemistry classes and you need to know this. So you see that this is 1s2. So let me write in the periods. So this is period 1, period 2, period 3, 4, 5, 6, and 7. So as you can see, it says 1s2. So what does that represent? That at level 1, I have 1 box and 2 boxes. So think about it in like the analogy that I like to use. This is kind of like playing any board game, Monopoly, Chutes and Ladders, for those of you that have siblings or nieces or nephews, in which you are taking, counting the boxes. But in this case, you cannot skip. You always have to, start at the corner of 1s and then land on the number of electrons that you have for that particular atom. So here, this area where it says 2s2 is because at level 2, we have 2 boxes. This 2p1 is this area because at level 2p, to get to boron, we only have 1 box. So that's where the numbers and letters come from. The only thing that at times is confusing to students is once they get into those transition metals, and then they forget that once you get to the transition metals, the period actually drops 1 level. So after 4s, you don't have 4d, you have 3d. And once you walk through that area where you start at scandium and you add zinc, if you have an element that have electrons that land in the 4p, understand that at level 4, in the p orbitals, the period number goes back to the value that we started with in the corner. So what I mean by this, just in case people don't see it, is that here is 4. Give me a moment, let me utilize. So this is 4, and you see that this is 4s. But look, here, this area is called 3d. This area is called 4p. So even though everything looks like it's on row 4, understand that the d orbitals actually, it has been shown experimentally to be at level 3. This is all based on laboratory data, okay? So what you mean is like, does 3D start after 3S? Is that the question? Okay, no. What happens is, again, this is all based on experimentation. What physical chemists have discovered through the years, understanding the population, because all of this is mathematical, but also they see it in terms of energy that is being released from the electrons and all that kind of good stuff. So in the book, because let me specify that in the book, they don't talk about electron configurations, they talk about electron arrangements. So please, when you look at this concept, do not utilize the textbook that we have in this course, because this concept of electron configurations is not discussed. Let me just establish that. Now, when it comes to the question that was asked, it has been observed that when the electrons are populating, first they populate 4s, then they populate 3d, and then they populate 4p. So for example, if you look at example number 4, okay, let's just establish what is that element. What is the element on number 4? How many electrons we have there? 37. Excellent, Gina. So what element are we talking about? Thank you, Gia. Exactly, rubidium. Rubidium lives here, okay? So what that means, think about it in terms of how things are populating like a particular area. The way that we visualize these electron configurations is that the electrons need to live in different energy levels, right? So to get to rubidium, we need to say, where do those 37 electrons live? Okay, so you see that there's 2 of them that live in 1s2. There's 2 of them that live in 2s2. There's 6 that live on 2p. There's 2 that live in 3s. There's 6 that lives in 3p. There's 2 that live in 4s. There's 10 of them that live in 3d. There's 4 of them that live in 4p, and there's 1 of them that lives in 5s. Because all we did in this process of writing the electron configuration of rubidium, which as you can see has 37 electrons, is that we say, what are all the boxes that I need to count before I land in rubidium? So that means that, let me just use another color, maybe yellow would do, that this whole thing is when I count. All of these boxes up to rubidium. Now, let me specify, because since in this course, we don't go in depth into explanations about chemistry. It's not that the electrons live in hydrogen or live in helium or live in lithium. We are utilizing the periodic table in order to say where the electrons are in a particular element. We are just utilizing the periodic table as a location map. We are not utilizing it in terms of the elements that are written in it. Let me specify that because I don't want you guys to be confused by that instance. So, any questions when it comes to electron configurations and determining the element symbol, or how many electrons are in a particular electron configuration? Because if you guys understand that concept, you will be able to answer this in the exam. Any questions?
Professor, I have one.
Yeah, go ahead.
What was the thing that you said earlier? I was kind of confused on it. You said something about understand this, like that, like a disclaimer or something, so that we don't get confused. I forgot that part.
Unless you're specific, I
sorry.
So
it was
many
like it was
disclaimers
just
here.
it's just
Like,
the thing
when
that
it
you
comes
talked
to that,
about. It was just the thing that you talked about earlier about the elements on the table or something.
that sometimes students, by looking at this, Thank you, Francisco. I think it was the comment about, was it the comment that this concept is not in the textbook?
Maybe, I'm not very sure, sorry.
So anyways, let me just repeat it really quick. If you guys look at electron configurations as a concept in the textbook, it's not there. What they have is electron arrangement. And electron arrangements and electron configurations, they're cousins, but they are not the same thing. Electron arrangement tells you at each of the different periods how many electrons live there. That's what electron arrangement does. Electron configuration tells you which floor you live, where's the apartment, that will be the letter, and how many people live in the apartment. That's where you get as an exponent. I always like to use analogies. Hopefully my analogies don't confuse you guys. So when it comes to electron configurations, there's more detail. It tells you what level, what shape, and how many electrons.
Okay, thank you. Thank you so much.
No problem. Any other questions?
Oh, yeah, I have a question. I remember you said that the S configuration is a circle. What do the other letters look like?
So what happens is that the S configuration is the circle. And then when it comes to the shape of the p orbital and the d orbital, these are going to be lobes. So it's kind of like pear-shaped images. So if we look at them closely, see how they look like more like an oval? So these lobes, which is the technical term for them, in the p orbital, there's two. And then this is based on some complex mathematical equations, which thank you, Lord, that I didn't have to take physical chemistry when I was a student. But all those souls that had to take that class, they survived it. These lobes are based on those 3D graphs that come from actual equations. So in the p orbital, we have 2 lobes. In the d orbital, we have 4 lobes, but you can see like in the third one, it adopts something interesting. And then on the f orbital, I think there's 8 lobes. And you guys don't need to know the shapes. Like in terms of this, I'm not gonna put one of these shapes and be like, is this an f orbital? I don't ask those kind of questions. That's too simplistic. For me, it's more important that you guys, if I give you a particular electron configuration, you're able to tell me, okay, this electron configuration is corresponding to this element. And in the next topic, if there's not actually another question, we're going to see how electron configurations actually tell us a little bit of more information of each element. Any other questions before we proceed? Great. Since there are no other questions, there are a few more things that we need to discuss when it comes to these concepts. The next one is group number and valence electrons. So this is the short story out of the whole thing. We already know what the group number is. Remember that that is going to be the number and letter that we see on the columns of the periodic table. Now, understand that when it comes to valence electrons, the valence electrons by definition are going to be the electrons that live in the outermost energy level. Okay, so that means that if you think of the system of the rings, if we are thinking like in the Bohr model, the electrons that lives in the outermost ring. Okay, now when it comes to group number, we don't even have to use electron configurations to determine the valence electrons of an element, because we know that for representative elements, the group number tells you the number of valence electrons. And remember, representative elements are going to be specifically group 1A to 8A. Yes, noble gases have the most valence electrons in its outermost shell. They actually have filled valence electrons. Now, as you can see here, group 1A has 1 valence electrons. Group 2A, 2 valence electrons. 3A, 3 valence electrons. 4A, so on and so forth. Now, you can see that there is a trend up to 8A. Now, there is an exception to the rule. Like many times, you guys are going to hear me say that. When it comes to the exception to the rule, helium out of 8A is the only one that doesn't fit this rule of 8 valence electrons, because helium only has 2 electrons in its outermost shell. Okay, now this concept of, again, valence electrons and group number only applies for representative elements. I already highlighted, but I'm going to underline it. So whenever you make these assumptions, your elements have to be on groups 1A through 8A. And you need to understand that there's an exception to it, okay? Now, if we utilize the electron configurations to actually understand this electron, the valence electrons, let me just bring back the concept that we just studied, okay? And understand that this is a copy of the markings that I did before. You will see on the notes, if you go back to it, that you are not losing any data. Don't think that, oh no, she erased it. It's there. You will see it there. So I'm just gonna cross this out. And we're going to look at valence electrons. So you guys see the correlation of what I just introduced to you. So I already showed you the shorthand, right? We already know. I'm just going to write the symbol. This is boron. This is silicon. This is titanium. And this is rubidium, okay? Put in the chat, what are the 2 elements that are representative elements? Put in the chat the 2 numbers for the elements that are representative elements. Out of these, who are representative elements? Excellent, boron and rubidium. The group number for boron is 3A. Rubidium lives in group 1A. Again, I already showed you the shorthand, so I know that you guys will be able to answer in the exam. Oh, I learned in class that boron lives in 3A because it's a representative element. That means that it has 3 valence electrons, okay? Now, if I look at the electron configuration, we can even tell where those 3 valence electrons live. Why? Because when we look at this, these 3 valence electrons, because it is the outermost shell, that means that the outermost is the largest digit in the period value. For boron, it's going to be level 2. Put a 1 in the chat if you understand that, or do I need to repeat myself? I just want to make sure that people caught what I said. I only see a few ones. Excellent, I'll repeat it. So remember, valence electrons are going to be the electrons in the outermost shell. So when I look at where the electrons are in my boron, there's some in the 1s, there's some in the 2s, there's some in the 2p. But I need to focus on what is the highest period that I have. What is the largest digit before the letter? And as you can see, we have the level 2. Okay, put a 2 in the chat if now it makes sense.
Professor, are you talking about like the circle, like shell figure in slide 16? Is that how you're figuring it out?
No, remember that I'm talking about the period. So what I'm talking about is these digits. That's where those numbers came from, right? So if we go back to this, look at where the purple is. It's because those are 1s. So I'm talking about the digit 1 before the s. Or I'm talking about the digit 2 before the 2s. Does it make sense now? Why I'm looking at the 2? Because I'm comparing something that is in the first floor, meaning 1, and then the letter S, or things that are in the second floor. Let me do drawings for those students that are more visual learners. If I have boron, and I need to use the analogy of like, oh, boron, the electrons in boron live in 2 floors. The first floor is the 1s floor. The second floor in this building has a corner that is called 2s, but a corner that is called 2p. Let me just do the drawing a little bit better and clear. So this is my apartment building where the electrons of borons live. In the first floor, I have 1s. In the second floor, I have 2s and 2p. Put a 3 in the chat if that makes it more clear. For the students that still are having trouble with this, after class today, I'll be able to, explain it again. But what I'm trying to illustrate now is that we understand that boron has 5 electrons. Where do they live? It has 2 electrons in the first floor. Give me one moment, because this moved. I didn't want it to move. It has 2 electrons in the first floor. And then in this room, there's 2 electrons. And in this room, there's 1 electron. So the valence electrons is the ones that are in the outermost shell, meaning the top floor. I hope that that analogy helps. So I'll answer the question in the chat in a moment. So right now, what I'm trying to illustrate is that those 3 valence electrons in boron is because they live at level 2. Some are in the 2s and 1 is in the 2p. So that number 3 comes from the addition of the 2 electrons in the 2s and the 1 electron in the 2p. Okay? So let's utilize that concept and understand that, hey, rubidium has only 1 valence electron. Where does the 1 valence electron in rubidium lives based on its electron configuration? Let's put it in the chat. Excellent job. The one valence electron in rubidium lives here. Because when I'm looking at the building where rubidium is populating its electron, let me just draw it here. This is a larger building, you guys. It's gonna look kind of funky. Sorry that maybe architecturally, this thing is going to be looking kind of funky. So at level 1, we have 1s. And at this level, we're going to have the 2s and the 2p. And then at this level, we're going to have the 3s, the 3p, and for the purposes, okay, not of how they filled, for the purposes of illustrating this, let's say that the 3ds are right here. In the 4th level, we have 4s and 4p, and for the last level here is 5s. Okay, let me just write this. Just for illustration purposes. Okay, so again, when we're talking about valence electrons, is whatever electrons live in the top floor, the last floor. So this is 2, 2, 6, 2, 6, 10, 2, 6, 1. So these are the valence electrons. To answer the question in the chat, it gets tricky once we're talking about the elements in group B. So that's silicon, that titanium. And the reason why, well, silicon, not so much. Titanium is the one that gets more complex because in titanium, since it is a transition element, okay, then sometimes transition elements are, they like to sometimes give 1 electron, sometimes give 2 electrons, and we're going to see in chapter 6 how they have, you know, the ability to give what they want when they want. Okay, so titanium, because it's in group B, is going to have different valence electrons. So technically, according to the rules that I'm introducing to you guys, in titanium, there's 2 valence electrons in it because of these. So technically, we say that it has 2 valence. But when we look at the group number where titanium is, you can see that titanium is in group 4B. So I don't want you guys to be thinking of like, oh, it's group 4B, so it has 4 valence electrons. Once you're talking about the B group, the rule doesn't apply. Now, when it comes to silicon, silicon actually is part of the representative elements. So what is the group number for silicon? So silicon is a representative element. Even if it's a metalloid, it is still a representative element. What's the column where silicon is? Great job, 4A. So how many valence electrons? 4 valence electrons. So where are the 4 valence electrons living? Great job on period 3. People are getting it. I'm so proud of you guys, because this is a concept that sometimes can be hard. So these are my valence electrons. There's 2 that live in the 3s and 2 that live in the 3p. So understand that for the exam, if you're given an electron configuration and I ask you how many valence electrons, you guys will be able to tell me where do they live, because I went over it in class. If you're prompted to just say, hey, how many valence electrons are in this atom, then you will, again, look at the group number as long as we're talking about representative elements. 1A through 8A. The digit before the letter A is the number of valence electron, and remember that helium is the only exception to the rule. Lastly, when it comes to valence electrons, we can illustrate those valence electrons by writing the element symbol and writing dots around them, okay? So the valence electrons are illustrated in what are called Lewis structures. And remember, in Lewis structures, we're only looking at the valence electrons. Now, you can see here in the example of aluminum. Aluminum lives in group 3A. So it has 3 valence electrons. How do we illustrate those 3 valence electrons? You can see it here. We write the symbol for aluminum, and then we write the dots around them. Now, in this class, we don't look at the structure of the atoms until the next chapter. So far, understand that in this class, I don't prompt you guys to know how to write the dots. Make sure that you count the dots around the element symbol. Any questions about electron configurations and valence electrons and electron dot symbols? Great question in the chat. So if you need to find the valence electrons for group B, similar to what I did in the example here for titanium, we do the same exercise. You look at the highest floor. And if you look at here for titanium, look, we have 1, we have things in the 2, we have things in the 3, and then we have something in the 4. So technically, that's why we say that there's 2 valence electrons. Group B are tricky to explain in Chemistry 104 because we don't go in depth into this concept. So for the most part, I tend to just leave the explanation to you guys around just the representative elements. So let me correct what is in the chat. So silicon needs to have 4 valence electrons. Again, if I utilize the whole idea of, my drawings, and I'm sorry that I know how to draw molecules and that's about it. I hope that this analogy of these interesting buildings is helping you guys. Think about silicon. Silicon has, is housing its electrons in a 3-floor building. It has 2 electrons in the first floor. It has 8 electrons in the second floor. It's just that there's 2 people in one apartment and 6 in the other. And then on the 3rd floor, it has only 2 apartments in which each of them are occupied by 2 people. So silicon has 4 valence electrons, not 2. There's one more question in the chat. So tellurium actually has 6, right? Tellurium lives in group 6A. So it has the 2 from the 5s, and it has the 4 from the 5p. So tellurium lives in group 6A. Oh, tectinium. Tectinium will have the 2 from the 2s. But again, when it comes to it's the complexity of this, like I said, when it comes to group B, we're doing the same exercise. When it comes to this class, I don't write in exams for you guys the transition metals because the chemistry is more complex. I tend to just stay within the representative elements because that's a little bit more straightforward on the discussions that we have. For those of you that have to take other chemistry courses, trust me, they're going to explain in detail why is it that we have a certain number of valence electrons for my transition metals. Great. I want to do at least one of these before I finish up because it's already going to be 11 o'clock and I'm soon going to need a break and I'm sure you guys need one too. So let's do at least beryllium, okay? So how many valence electrons in beryllium? Great job. Beryllium lives in group 2A, so there's 2 valence electrons. So if we're going to do the electron dot symbol for beryllium, we write the symbol and we put 2 dots. The reason why I pair the 2 dots is because typically in chemistry, whenever there are electrons, we pair them if there's 2 of them. But understand that right now, because we haven't learned structures, which is one of the things that we will be dealing with next week, we are just going to count the dots around the symbol. Any questions? There's only one more topic that I want to talk about before we go on break. Excellent. So the next topic that I want to mention is the last concept that we need to study in chapter 4, which is going to be the trends in the periodic table. We have already seen how the periodic table has so much rich information that we can derive from it. And we observe how electron configurations, additionally to all the other concepts that we have learned, are very important. But you can see that the electron configurations are particularly important because it is the factor that is taken into consideration for looking at the properties of elements in terms of their atomic size and metallic character. If you look at section 4.7 in the textbook, there is another trend that is called ionization energy. You guys are not responsible for knowing ionization energy. So the only 2 trends that you guys need to know are atomic size and metallic character. And these are the trends. Let's start with atomic size. So understand that for representative elements, the atomic size is going to be going down as we are moving from left to right in the periodic table. So as we're moving across, look at as we go from lithium to beryllium to boron to carbon, so on and so forth, all the way to neon. The atomic size gets smaller. That's the trend. Atomic size decreases as you move across a period in the periodic table. Now, if we look within the groups, let's say, for example, we observe group 1A, we see the atomic size is going to increase. This is how we rationalize this particular concept. So I utilize a lot of analogies when it comes to this. One of the things is that in the trend, when we are looking across a period, when we're moving left to right, we see the atomic size is getting smaller. But if we look at the atoms, they're actually increasing in the number of electrons and the number of protons. The technical explanation says that since we are increasing in electrons and increasing in protons, basically the protons are going to be pulling those electrons and making them tight. This is how I rationalize it in terms of an analogy. If we are lithium and we are in a space, think of if you have taken classes face-to-face at any school at any point, it's kind of like you are by yourself entering a classroom. So the classroom is going to look really big. Now, as we move from left to right within the same period, is because the number of electrons and protons are increasing, it's kind of like more people are entering the same room. And when more people enter the room, don't you feel that the room feels smaller? Well, that is the trend that we see in the periodic table. When we look at the group, meaning the column, when we look at group 1A, see how it says number 1 for period 1, period 2, period 3. So as we move in periods, okay, this is kind of like we are getting into larger and larger rooms where we are the first one there. So that's why the room looks bigger. So again, you can see here what are the trends for atomic size in the periodic table. When it comes to metallic character, a little bit of more straightforward metallic character, because when it comes to metallic character, similarly to what we saw in atomic size, decreases as we move from left to right within a period. And in a way, it makes sense, because when we look at it, we can see that we're going from the metals to the non-metals. So of course, the elements that are on the right side of the periodic table are going to be less metallic than the ones on the left. So that's why metallic character is decreasing. Now, when it comes to metallic character as we move down in a group, let's observe group 4. We start with a non-metal, which is carbon. And as we're moving down within that group, we can see that we're getting into elements that are metal. We go from a non-metal to metalloids all the way to metal molecules. So that means that metallic character increases as we're moving down within a group. And it can be illustrated better in some of the groups in the periodic table. So we can see it clearly, for example, here in group 4A and group 5A. And those are the two trends that you guys need to know. Any questions when it comes to the trends in the periodic table? Excellent. So this completes all the material that we need to know for exam number 1.